Good morning, everyone. I hope you is having a good time attending summer school. In this section, I'm going to briefly talk about NLP and its application. I think this session would be a bridge between what you learned on Tuesday and what we are going to learn for the deep learning session. And so, to begin, I'll just briefly discuss how natural language processing is defined. So natural language processing, or how people usually call it NLP, is a very popular, successful, and important topic in computer science, partly because we deal with textual data all the time. A lot of textual data are being generated through social media and news outlets, through news articles from papers or transcripts, and also research papers by scientists. So by having a ton of text on hand opens for us a lot of good opportunity to better understand individuals, communities, by analyzing and representing text with automated methods through NLP approaches. And researchers also strive to develop methods so that computers can better understand natural language, which is a very challenging task, and we'll explain why it's so challenging. And also, there are others, many specific applications of NLP, such as machine translation and speech recognitions that we use every day through our mobile phones or computers. And NLP problems are hard. So if you remember, on Tuesday we're working on a dataset called Iris. So it's a more structural tabular data, but for natural language is unstructured. So we have to transform the text into some machine readable form so that it could be processed by the computer. And on the other hand, it's very hard to develop computer programs to achieve human level language understanding in nature, because as a human, there's a lot of things that we do intuitively, but it could be very hard for a computer to read or to understand. So to make a very obvious example, it's relatively easy for us humans to understand sarcasm, but it's very hard for computer programs to read the room. And before deep learning have become a very popular or successful methods, tasks such as very accurate translation is unimaginable. So I can still remember the first translation software I used, and it was terrible. But recently, because it appears that deep learning has become a very successful and also popular method to solve NLP problems, a lot of the tasks become better. So languages are unstructured, and some tasks are hard for machine. On the other hand, natural language is very rich. There are many different levels of natural language, and in each levels there could be variable for us researchers to understand in order to further understand individuals or communities who generated those languages. So in order to face the challenge, the field of NLP usually gather power from different fields. And as I mentioned, since deep learning and machine learning has proved to be very successful, more and more researchers with statistics or computer science background is collaborating with linguistics and cognitive psychologists to develop methods for tasks usually originally proposed by linguistics. And people from many different fields are also interested in applying those methods in their own field. For instance, for social scientists and for sociolinguistics. The most obvious example would be sociolinguistics, who are interested in applying automatic methods or NLP methods to their own task. And then the field computational sociolinguistics was born. And to give a sense of how successful machine learning and deep learning methods are, I'll give a very realistic example. So, well, it was a joke by Untitled, but the joke was made to urge researchers to make use of the insights from linguists. And there are a lot of applications for NLP. For computational social scientists or data scientists, it would be very useful to make use of the text generated on social media and to understand the sentiment of people posting on those platforms. And there are also a lot of other applications that people that are not researchers could make use of and benefit from. For instance, auto-correction, machine translation, speech recognition for smart assistants. And in the realm of science, applying NLP methods is also very important because we're dealing with a lot of text. So writing a research paper and submit it to a journal or a conference is a way researchers communicate with each other. And in that process, in order to decide whether a paper is worthy of publication, there are exchanges between reviewers, editors, and authors. And in that process, more texts are generated. And when we apply for grant, we write proposal. When a doctoral student like me graduates, I have to write a dissertation. And NLP method is important also because we're dealing with more and more text. So this visualization shows that an exponential growth in the volume of scientific literature. We need to, so it's growing faster and faster each year. So it shows that why it's important to not analyze those texts manually, but rather develop automated process to processing those scientific texts. So in the realm of science, there are many applications of NLP. The first I heard from either the first day or the second day, a lot of people are interested in citation context analysis. So in those tasks, researchers analyze whether a citation is worthy of being cited, and the sentiment in that citation context, and whether people cite a citation only because is published by someone who have a very high H index or from a very good school. And from the citation context, whether there's a citation bias. And the other application is paper recommendation. As we show in that visualization, we can see that there are a lot more papers produced each year nowadays. So it's quite hard to find the exact paper that we need. So it's very important to develop a system who could, based on your research interests, recommend a paper or a funding opportunity. So in that case, it's very important to develop accurate paper text representation. And because there are so many papers, we cannot, it's not practical to read through all the research papers. So it's important to develop methods that could manually, automatically process the publication and generate summarization of that paper. And because, as I mentioned, there is an exchange in the peer review process between peer reviewers, editors, and authors, argument mining would provide a very interesting aspect for us to understand how that process works. So in the following slides, I'm going to briefly introduce how language are represented in a machine-readable form, and then I will walk through the notebook to show how you can do it yourself with Python. So first, I'm going to introduce the sparse representation of language is also called the back-of-word model. So to create a sparse representation, we first tokenize the text into tokens. And then we decide how we count the tokens and represent the text into what we have count. So at the end, we have a numerical vector representing the text and is machine readable. So in this process, we need to tokenize and vectorize the text. To tokenize the text, we need to consider how we should split the sentence into tokens. So as we can observe here, different tokenizers behave quite differently. So in this example, if we look at the sentences in a slice, and there are many different ways it could be tokenized. And the main difference here, I think, would be how the tokenizers dealt with the apostrophe and the punctuation. So after deciding what to count, vectorizing, we will need to decide how to count. So there are also many ways that we could count the tokens. For example, in the example that I show above, we're basically counting the word frequency or term frequency. But instead of doing that, we could also count whether a word is in a sentence. So we put a 1 in the vector if we found there's a word in the sentence, and put a 0 otherwise. And sometimes we're working with corpus with sentence of very different lengths. And sometimes we don't want the length of the sentence affect the sentence representation. Because for sentence with a longer sentence, there should be larger word term frequency for most of the terms. And that could affect and differentiate a longer sentence with a shorter sentence. In that case, we will consider using normalized term frequencies, in which case we divide the term frequencies with sentence length. And another normalized term frequency would be TF-IDF, is term frequency inverse document frequency. So sometimes in a corpus, there are terms or words that appears almost in every sentence, in the sense that counting whether the sentence or the term appears not in a sentence wouldn't contribute much information to the task you were worried about. So by using TF-IDF, if a word appears in every sentence, we will have a very small, tiny value in that vector that we generated for the sentence. So the back-of-word model is a very effective way to represent language in a machine readable form. But by using it, we are also losing a lot of information from the words, for example, semantic information. For instance, with the representation, the computer cannot tell the relationship between man, woman, king, and queen, because for them it is just a 4-dimensional vector with 1 and 0s inside. So as built by the computer, the differences between man and woman are equal to the differences between man and king. So this is not a very accurate semantic relationship that could be inferred from computer. And it cannot tell how they're different and how they're similar. And on the other hand, to build a back-of-word representation, a sentence vector could be very large. It could be as large as the size of the vocabulary of the entire corpus. So for here, we're dealing with 4 terms, but imagine that you were trying to tokenize and vectorize an entire book. The size of vocabulary could be thousands. So sentence representation could be as large as 1,000. So if a word in a corpus is not in a sentence, we still put a 0 there for sentence factor. A deep learning-based method called virtual vector could create dense representation of words, and each word is mapped into a fixed size vector. The vector with continuous value includes semantic information of the word by when the model is trained, it looks at the words after and before the word. So to create the semantic information of that central word, so that we could do calculation like this. Next, we'll walk through the notebook. So in the Jupyter environment, when we go to lectures under deep learning, there's a notebook called Notebook NLP Text Mining. Oh, by the way, so far, is there any questions? Yes, those slides, I'll make them available. Okay, so let's do a walkthrough of the notebook demo. So in this demo, you are all familiar with using the two NumPy pandas and scikit-learn. So the first example here so scikit-learn is powerful in the sense that you have the power to process different forms of. Do you mean the display of the notebook? So if I do this, will it help? Okay, okay. Okay. So with scikit-learn, we can actually do both tokenizing and vectorizing text. Just we need to know images. And in this example, we're using a dataset about citation worthiness and could be downloaded from Figshare. And because it's a relatively large dataset, we'll just work with the training split, but in reality, it has both a testing and verification split. So we check the size of the dataset. Hopefully the environment won't crash. And as seen here, the percent here is the citation context, and the cur has citation is the label for whether it's making a citation. So convector and DFID vectorizer are two vectorizers that we can use to vectorize text. So by adjusting the parameters, we can adjust how the vectorizer do the counting. So if we set the binary to false, it means that it's counting the word frequency. And on the other hand, if we set it to true, it's just counting whether a word appears in the sentence. And we can also adjust the n-gram. So by n-gram, if by default it is counting the process of tokenizing, each word is a token. But if we're counting 2 grams, a token could have 2 words. So if I set the n-gram to 1 to 2, is counting 1 gram and also 2 gram, or bigram and unigram. And by setting stop word here, the vectorizer would automatically remove stop words, which contribute almost no information to sentence. And in most of the tasks, we'll just choose to remove those stop words. So in this case, we are using the unigram count vectorizer, which count the term frequency of sentence in the entire data set. It should take a moment. Okay. So I'm printing the shape of, so the word vector is the vectorized vectors. As you can see, it should be a sparse matrix. It's a sparse matrix because it's huge. So you can see the width of the matrix. This is basically the size of the vocabulary of the entire corpus. So now I'm picking the first vector from the matrix. You can see there's a lot of zeros here. So that shows a reason why sometimes we need to pick a more compact representation of words instead of the vector point model. And here, by printing the vocabulary attributes, it shows the vocabulary of the entire corpus. Now let's go on to creating the dictionary. I'm not sure. It should take a minute. I think you can try it on your own, but it should take a few minutes. Oh, anyway, I'll just run it here so that I can show. I think it's now a good time for me to ask if there's any questions.
I had one question.
Yes, please.
So up above, you put in the stop words, which, as I understand it, are things like the and of.
Yes.
So does that mean you're ignoring them? Because then further up, when you printed out the entire vector, I saw the and of. Can you explain that?
Sorry, the last bit.
If you scroll up a little bit more, up.
Yes.
Yeah, right here. Up, down. Sorry, too far.
Here.
Down. When you print it out, when you can rebuild down a little bit more, please. Down here, 17. So I see the word the and of. I thought those were stop words, so those would be ignored. Is that not the case?
Mm-hmm.
In the output of 17?
Yes, so in that vectorizer, I didn't remove the stop word. So yes, some of them, they are different vectorizers. I put them as an example. But feel free to try them out, like replacing the other vectorizers with these vectorizers with other vectorizers and try out the classification first.
Okay.
So in these vectorizers, it's not removing the stop words, but we can also try that. So this is removing the stop word, and it's background. Finish training. Yeah, we can try that out after you finish training.
In general, do you recommend removing stop words, or how do you advise going around the fact that the appears so many times?
I think it depends. I think in some corpus it's important to remove them, and in some cases it's not. I think for other tasks such as topic modeling, because word frequency or frequency distribution matters, in those cases, I think it's more important to remove words that don't contribute a lot to semantics. But in general, I think on Tuesday we introduce cross-validation. I think we can build both. With one case, we remove the soft words, and the other case, we do not remove the soft words. And at the end, we just compare the validation score to see which feature will be better. As it is running, I think I will continue to work with. I think I wanted to train the model is because I wanted to show how we can interpret how the classification is working by showing the most important word tokens, by showing the feature names, the tokens alongside with the size of this coefficient in the model. So it's possible because we're using logistic regression, it's a relatively easy model and we can interpret them. And similarly, we can do the same with random forest because we have something called feature importance. And in this demo, I also tried out TF-IDF, which is also a normalized form of the term frequency vectorizer. And this should improve the performance of the classification task. And a thing that we can discuss here is that by creating the backup word representation of words, we're actually not regarding the order of the word. So if a sentence A with a set of words and sentence B with the exact same selection of the words but with different order and possibly with different meanings, represent the model will the two sentences as the same sentence. And today in the section talking about deep learning, we will introduce RNN, which basically solve the problem. Okay. Anyways, as I introduce the part here, I'm not sure if I introduce it clearly, but basically we just need to understand how we need to interpret the classification model to show like which token is most important.
So maybe, Lijian, if
Yes.
if you kind of limit the number of iteration that might finish sooner,
Yeah.
maybe you put max iteration 10 or something, or 5, just to see.
Yeah.
Maybe one finds something good, but hopefully,
Yes.
because
yeah, I guess
there are
I
lots
just
of
did it. Yeah.
Yeah, so let's see what it found.
It's not
Yeah,
bad. Yeah, the performance is actually not bad. And so at the end, you will have data frame and a data frame like this. So somehow the most important word token is off. And num is negatively related to whether there is citation in a sentence. I think at the end we'll still need to, yes, please.
Maybe put a couple more iterations. I think you use 5 and let's use like 10 or 20. But they still make sense because you have the features. The most important one is based. So if you're writing a paper and you say, this is based on, you're usually going to cite someone.
I don't think the accuracy makes sense. Yes, so as we increase the number of iterations, the model converge better a little bit. And you can see something totally different.
No, but that makes total sense because when you write a sentence in a paper and you say see, propose, similar, you basically are going to cite someone, right?
Yes, that's true.
But when you're talking about a table or a figure, you don't need to cite someone. You're just going to put that reference to your own paper.
Yeah, that's true.
So that's the negative words make a lot of sense.
I see. Yeah. So the feature importance or the interpretation model actually provides a lot of information for us to interpret why a sentence is cited or not cited. But I think at the end, as a researcher, we still need to go back to the corpus to understand exactly why. But interpreting a model do give us a lot of power in studying the entire process. And so maybe I think it would be also fun if you can try yourself to replace this vector to other vectors that I listed here and to look at the vocabulary. I believe that with this vectorizers, we remove the stop words. Then I will try to introduce a Python package called spacing. So I don't think it's installed in the environment. Every time it starts up, it removes the packages. So you need to install. So in the lecture, I mentioned that there are a lot of applications and there are a lot of different scientists from different fields trying to tackle problems posed by the linguistics. But so there are a group of researchers who, like computational scientists, who are more interested in applying those methods in solving problems. But there are also a bunch of researchers who are interested in developing those NLP techniques. And because there's already someone who have worked in there, we don't have to develop our own NLP or train our own NLP models. So by using Spacey, we're basically using other people's model to analyze our own text. So here we put the package and load a pre-trained pipeline. So someone else have trained the pipeline so that we could make use of the functionality that we'll see. So NLP is an instance that is a spacey pipeline. In order to use it, we pass a sentence to the pipeline, so it could create a spacey document instance. So this is what I pass in is just the first sentence in the training data set that I just mentioned is a string. But after processing, is a spacey document instance. And after we pass the string to the pipeline, it actually went through a lot of processes that the program process for us. So if we to give you so there are a list of different functionalities the pipeline provides. For example, the lemma is basically the root form of each token in the Word document that we pass in the NLP pipeline. And the pipeline also provides post-tagging, and it predicts whether a word is alphabetic and whether a word is stop words. So instead of using a data set that we just import, I think it's also interesting to use tags that are more relevant. So in this case, I'm retrieving using OpenNX API the relevantness size of science review. So I just retracted the abstract from the inverted index of OpenNX. So this is the abstract of a scientific publication retrieved from OpenNX. So spacey also have its own tokenization, something like this. So in the different levels of natural language, there's morphology, which is related to the form of the word. And lemmatizing is the process of reducing the reflective forms. It gives us the most basic form of the word. Somehow it doesn't work here. And Space also provides tools that we can use to get the word frequency of a document. We also have a function of also have a list of its own stop words, and we can show that what are those stop words. And I've shown a more general functionality of what spacey pipeline could do. And it's actually the attributes of each token in the spacey document. And sometimes, for example, for abstract is too long, we want to break them into smaller chunks so that we could process those chunks more accurately. And spacey have functionality to break longer piece of documents into sentences. And there's post-tagging, is associate each word in the text with its correct lexical syntactical category. Is important because syntax expresses the way in which the word are arranged. So it's often used in many different NLP tasks, such as information retrieval and word sense disaggregation. And dependency parsing, which is also a very interesting functionality of Spacy. It's a grammar that represents the dependency relationship between words. And it visualizes it quite nicely. And Spacy also supports an NDR and entity definition. And as I mentioned in the slides, the Spacy pipeline also supports pre-trained word embeddings model. So we can have a sense of how the dense representation works. So here I'm passing man, woman, king, and queen in the pipeline. So here each of them is instance. So each token have our vector. So by counting the cosine similarity or cosine distance of those dense representations, it shows how two words are semantically similar. So under the hood, similarity is cosine similarity. And we can do the same calculation that I showed in the slide. And by default, if you pass the entire sentence to the NLP pipeline, and if you call the vector feature, it will just automatically return the average word embeddings of the entire sentence. And we can show here those two sentences are very similar. And if we want to calculate the similarity, under which is cosine similarity, is 1, because those two sentences are semantically the same. And I think more dense representations like word embeddings are very useful tools because it contains a lot of semantic information and of course, and it dramatically reduces the feature dimensions. So I would encourage you to try it out yourself and using the word embeddings to try the classification task that I mentioned about. And is there any questions? Thank you.
Thank you, Lijian.